today we are going to talk about classification, and we have two different lectures for classification. The first one will cover the classical approaches, which were there before deep learning. And then we will talk about how classification can be solved using deep learning approaches. Okay, so we have two different lectures for the same topic. And this is the first lecture. The outline for this lecture will be, first we will briefly cover the basics of classification, and most of that we have already covered in this course in previous lectures. And then we will move on to like different kind of classification approaches which were there before deep learning era. And we will start with nearest neighbor classifier. Then we'll talk about maximum margin classifier. And finally, we'll talk about support vector machines. Okay, so let's start with the first segment, which is just covering the basics of classification. And as I said, we have covered most of it like in the previous lectures. So I will quickly run through these slides. And if you have any questions, you can later ask those questions. Okay, so the main idea of classification is, given a sample, you want to actually identify which class category this sample belongs to. And in that, you will have like some set of classes. Okay, so you'll have to choose one and say, okay, this sample belongs to this particular category. And one simple example for this could be like your, let's say, digit classification. You could have your data set where you have images of those digits, and digits will be from 0 to 9. And a simple classification problem will be given an image of the digit. You will say like which of these digits is present in that image. Okay. Now that will require, because we have like we have numbers from 0 to 9. So that will require like a 10-way classifier, because each sample could belong to either 10 of the either one of those 10 categories, right? So before moving on to like multi-label, that's called multi-label classification or multi-class classification. And that's like a more advanced scenario. But let's begin with like a very simple case, which is called binary classification. And in this case, the idea is you just have two classes, or even like a simpler case, you might have just one class. And the idea will be, for example, if the class is person detection, so you have to detect whether a person is present in an image or not. So you can solve that as either person is present, that will be one class. Person is not present, that could be the second class. All right. So the way it will look is now we know features, and features we know like it has like a certain dimensionality. For example, it could have like, let's say 10 different numbers, or it may have 1,000 different numbers. Okay, so that will be your features. And in this case, I'm just showing you features which are two-dimensional. Okay, so this is your Euclidean space. And all these dots over here are your samples. All right. And depending upon what's the X and Y coordinate, or you can say like those two are your features, where they lie in the Cartesian coordinate or your Euclidean space, you are just putting that point on that space. Okay. So in this case, the blue dots are, let's say, category number 1, and the orange dots are category number 2. And here you can see that you can actually draw a very clear straight line between these two categories. And if you remember, like from your algebra or maybe numerical analysis, like your high school maths, you know that you can represent a line using a simple equation. And if you have that equation for this line, that equation can serve as a classifier. And then you can put like each of these points in that equation of line. And depending upon what's the sign of that of the resultant value, you can estimate whether that point is actually towards the blue side or towards the orange side. And if the point is exactly on this line, then you will get perfect 0. Okay. So over this line, all points are perfect 0. And it could be like all the points towards blue are negative and all the points toward orange are positive. Okay, so in this case, this line, or you can say like a simple equation, is serving as a classifier. Right, so you can have like different categories of classification problems. As I said, you can have digit classification. So for that, we have MNIST dataset, and this is roughly like 60,000 images. And the images look something like this. So each image is corresponding to one of the digit. Right? And the classification task is given each of this image. You have to say which digit is present. And then again, we have a multi-MNIST. in that case, I don't have the samples, but it will look something like this, but you will have multiple digits on same image. Okay. And then again, we have this SVHN data set. Again, this is also digit classification. And these are, you will say, like more realistic images, because these were extracted from this HN represent like house numbers. Okay, so these were extracted from real house numbers, and you can assume that they will be very noisy. And again, but each of those images are actually corresponding to one of these digits, not as clean as this. Then we can have object classification. Again, we have several data sets here. We have CIFAR 10. It's called 10 because there are 10 different classes. Then we have extended version of that, which is CIFAR 100, where we have 100 different object classes. And then, of course, we have ImageNet, where we have billion of images. And again, there are different subsets of this. This standard one is like 1,000 classes. So if you have to solve the classification problem on this data set, it will be 1,000 classifier. All right, so again, classification, you can call that object recognition as well if you are interested in some set of object categories. And as we discussed earlier, a simple variation could be binary classification, where if you're interested in persons, the question will be whether person is present in the images or not. And your classifier should provide you this answer, either yes or no. Okay, so ImageNet, I think this is the most popular data set for image classification, and we have roughly 1,000 categories, as we discussed earlier. We have 14 million images, and I think this is growing daily. They are increasing the size. They're collecting more images, and we have roughly 100K testing samples here. So this is like a huge data set. Just training like simple architectures on this model, if you don't have enough GPU resources, it takes actually weeks. And in that sense, it's challenging as well. Okay, so those were the data sets. Now you understand the high-level idea of classification. Now the overall approach you take when you solve any classification problem is, given a training images, you have to separate those images into validation and testing. And again, we have covered these things before as well. So I'm going to quickly go over these. Okay, so the idea is validation. Images are something, when you train your model on these training images, you evaluate on these images, and depending upon whether your model is performing well or not, you can try to you can try to fine-tune your hyperparameters, right? For example, if you want to increase your learning rate, decrease the learning rate, or you want to change the number of layers in your model, if you want to use like more kernels. So all those hyperparameters you can change depending upon how your model is actually performing on this validation set. And testing images, again, you don't have like labels to these. They will be only used for evaluation. And you don't use like feedback on this test set to actually improve your model. Okay. So the learning phase will be, you will have your training images, you will extract features, and then you will train your classifier over here. And to train that, you know that you need the ground truth labels. In this case, classification, you will only need which object is actually present in your training samples. And that will give you like the training signal, which for which you can have a loss function. Okay. And at the end of this, you will get a train classifier, which you will run on your testing images. And again, for testing images, you will use the same feature extraction steps, and you will use the training model to make the final prediction. And of course, you will have labels for these testing samples, and you can evaluate how good your model is doing. So that's like overall training process, which you have to take. Now, let's quickly go over these features as well, what kind of features you can use. We can have raw pixel values. We can use directly those. We can use histograms, for example, HOG features or SIF features. We can have templates. And there are a lot of like other set of local features which are actually very useful for classification. And eventually we'll have, so this is something like which we will focus on this lecture. And we'll not specifically talk about these features because we have already covered like how we have to extract HOG and SIF features, right? Those are some of the variations. But what we will cover is how to use those features to solve the classification problem, because this is just the first step, right? And later on, we will see like, what if we don't want to use those extracted features? What if we want to learn those features? So in that case, that's the second part of this lecture where we'll talk about how, without extracting these features, we directly train your model end to end by directly operating on your input images. Okay, so whatever approach you do, the general framework is always a kind of a function where input is an image, where either you can just pass your image to your model, or you can extract features and pass those features to your model. And that model is going to make predictions about your images. Okay, so basically you have this function, which you can say a prediction function or a classifier. You'll have image features or the image itself, and y will be your output label. And again, you can, depending upon which method you're using, but this overall framework is never going to change. Okay, it still remains the same for whatever approach you use. Okay, so binary classification, as we said, you have to, given a sample, you have to just assign like one of the classes to it, because you only have two classes. And most of the time, binary classification is used when you want to say something is present or something is not present. All right, so again, these are your set of samples. This is like one category. You can say this is positive category, or this could be your negative category. And your classifier will look something like this line. We discussed this briefly earlier as well. So this is the simple case of binary classification. But what if you have multiple classes? Let's say you have crosses, then you have triangles, and then squares as well. So in that case, you can see that this simple linear line is not going to help, because you can't draw like a line to separate three different classes. Okay, so one simple solution could be you actually learn three different equations. And if you draw something like this, which is separating like these classes from one another, then your classifier is actually consisting of these three lines. Okay, so if you think about this, one simple way to solve this is, when you're learning this red line, so that could be your one classifier, and of course you can learn that function. What you could do is you can treat these crosses as the positive class, and then you can treat the green triangles and the blue squares as a negative class. So you don't distinguish between green and blue. You treat these as one classes. And then you can train like a binary classifier, which is the red line. And once that is trained, then that red line can actually tell you whether the red crosses are present or not. You don't care about like what are the other classes. You only care about red crosses. Okay, so that's like one linear classifier for you. Similarly, you can do the same thing for green triangles, right? And for that, let's say you learn like a linear line. And that line will learn whether green triangles are present or not. If present, you have these green triangles here. If not, you don't care whether it's like a blue square or a red cross. And similarly, you can do for the blue squares as well. So basically, if you have three classes, the simple approach you can take is you train three different binary classifiers. And you can use those to actually do multi-class classification. And that usually works like pretty well in most of the cases. Now let's move to the next segment. And in this one, we are going to talk about nearest neighbor classifier. It's a very simple classifier, and I think you will have a programming assignment for this as well. Okay, so let's quickly go over this, and you can see the name. It says nearest neighbor, right? And that's all the algorithm actually does. It just tries to find the nearest neighbor. So here's the idea. You have your training samples, right? And sorry about that. Okay, so these are your training samples. And you know that you have two different classes. Blue boxes is the first class, and red circles, that's the second class. And again, so think about this as you are projecting your features from these samples onto the Euclidean space, which means each of these point could represent like an image. Okay, and it could represent anything, like depending upon what problem you're solving. So let's say if this is an image, then you can extract features from that image, and then you can perform like some kind of dimensionality reduction. So don't worry about that. It's like an algorithm which maps your high dimensional feature space to small dimensional feature space, and PCA is one good example. We saw that like in I think the second lecture. And autoencoders is again, I mean, you can project it to a smaller dimensionality space, right? So consider that the case, then you are projecting that into two-dimensional space. And once you have two-dimensional space, you can actually just plot that on this Euclidean space. So each of these points could be an image. Okay. Now, how this nearest neighbor works, you take your testing sample. Okay, so the good thing about nearest neighbor, you don't have to train any classifier. Okay, so that saves your training time. The only thing you have to do is extract features. Now, you take your testing sample, and that testing sample, again, you will extract features, you will project, you don't have to project into this low dimensional space. You can actually work on high dimensional space as well. We will go to that later. But let's say this testing sample lies somewhere here. Now, if I ask you like, okay, to which category this sample belongs? So as a human, what will we do? We'll just see that, okay, I mean, this seems like it's closer to these samples, right? And it's far away from these red samples. So most probably this is a blue sample. And so that's the intuition. What we do is we compute the distance between this sample to all the other training samples. Okay, you will compute with this, with this, with this, and all the red samples as well. And then you can just sort all those distances. And whichever distance is the shortest, you just pick that class. So in this case, if this is closest to this blue sample, it seems like the closest one, then you say that, okay, this sample is from blue category. You just assign that blue category to this test sample, and that's it. That's your nearest neighbor classifier. All right. So now what I showed you is like projected on this two-dimensional space. But now let's think about, let's say you extracted features, and that feature is, let's say, 1,000 dimensional long. So you don't have to project, just compute distance in that 1,000 dimensional space. It's just like a L2 distance. You can use actually any distance, cosine distance, L2 distance, L1 distance. The results will not change depending on the method you use for computing distances. Okay, so you can compute distance in that high dimensionality space, and you just pick like the sample which is the closest and assign the class to the test sample, and that's it. In this case, that's the class. Okay, so that's the nearest neighbor algorithm. And as I said, it's pretty simple. And we don't need any training. All we have to do is extract features and compute distances from the test sample to all the training samples. Okay, so that's fine. I think we can skip the slide. Now the question is, what will be the decision boundary in case of neural networks? Because what we are doing is, given a testing sample, we're computing distances from all the training samples, right? So it turns out this is kind of a Voronoi plot, okay? And the way it will look like is, what's happening, so the red dot is like class number 1, the black dot is class number 2. Now, if you divide this whole space into like different categories based on distances, then all you have to do is you just divide two different samples. Okay, divide the space between two different samples. So this is a sample number 1, this is sample number 2, and this is like the line perfectly dividing these 2 points. Okay, so any point which is on this line, it's kind of equally distant from these 2 points. But if that point is towards black, it's black category. If it's towards right, that's red category. Okay, so you do that for all the pair of samples, and that will give you this Voronoi plot. Okay, and you can just you can just like do it manually. I mean, okay, so that's how the decision boundary will look like. And now what you can do is you can take any testing sample, and just depending upon like where it lies, in which regions it lies, you can just tell the category. For example, if it's on this block here, you know it's a black dot. If it's on the gray region, you know it's a red dot. Okay. And again, this is like just 2D. And again, that's in 3D space. Of course, you can extend similar kind of partitioning to n-dimensional space as well. All right, so there's a variation of nearest neighbor, which is called k nearest neighbor. And the idea is, instead of looking into just one neighbor, we actually look at multiple neighbors, and that value is k. Okay, because there might be some noise in your training data. And if the nearest sample you have that becomes noisy, then your classifier will fail a lot. Therefore, what we do is we look into like multiple neighbors. For example, if it's one nearest neighbor, that's fine. The case we discussed earlier, we just look at the nearest one. We can have 2 nearest neighbor or 3 nearest neighbor. Of course, we don't want to do 2 nearest neighbor, because then if there's a tie, we don't know what's the decision. That's why we always choose like odd numbers. And in case of 3 nearest, you will actually look into the top 3 nearest neighbors of the sample. Okay, and then whatever is like the dominant class category, you will just choose that. So you can have 5 nearest neighbor. So the simple algorithm is you have your samples, you extract features for the testing sample. And for each training sample, you compute the distance from the testing sample. And this is, I will select the most computationally expensive step, which is sort the distances. And you just pick like the classes based on top k samples. K could be like any number, 1, 3, 5, 7, or 9. It's up to you. So the good thing about k nearest neighbor, you don't need any training, and it's very simple and easy to implement. You will see like in your programming assignment, and it can be used for classification, regression, or search a lot of different problems. Now the issue is, so performance is one issue. It won't perform really well in most of the cases. The other issues are if you have a lot of training samples, then it will be very slow, because you have to compute distances with all those samples, right? And if your features are high dimensional, then again, computing that distance will take time. Now we are going to talk about maximum margin classifier. And again, this is based on like those decision boundaries which we were discussing for nearest neighbor. But we'll see like how we can actually learn them efficiently given a training data. So in nearest neighbor, there was no training involved, but in this case, we will perform some training so that those decision boundaries are actually learned. Okay. Now, the decision boundary, like what kind of decision boundary you have, that in some way defines what kind of classifier you will have. So the most basic could be a linear classifier. And the idea is you will have a linear boundary, something like this. And you know, like if it's a line, as we discussed earlier, you just need like 2 parameters to define this line, right? The slope of this line and the x or y intercept of this line. And just those 2 parameters define this straight line. So to learn a linear classifier, you only need to learn 2 parameters. Now, most of the time, what will happen is linear classifier might not be sufficient. And later we will see like how we can improve that further and introduce non-linearity into your classifiers. But let's hold on to that thought that will come into picture later. For time being, let's just focus on linear classifiers. Now, the question is, when we're trying to learn these lines, what should be the approach? Okay, so let's look at this example. In this case, again, we have 2 different categories. These are solid dots. These are hollow dots. All right. Now, we can draw this line. And again, as I said, a line, you just need 2 different parameters. The y-intercept and slope of this line. That's it. So this decision boundary looks like fine. So if you evaluate this classifier or this linear classifier, it will give you a perfect score on these training samples, because it's always correct for all samples. It's actually making the right decision. Okay. Again, this is also perfectly fine. Both will have 100% accuracy. This is also right. Now the question is, since there are so many solutions available, what is kind of a best solution among all these lines? And that's what we are going to do in this maximum margin classifier. Okay, so the question is, which is the best? So the approach to this is, what we will do, we will not just learn this line which separate these two different class categories. We will also try to maximize the margin between this boundary and the training samples. Okay, so let me try to explain what this margin is. The black line is the decision boundary. All right. And if you look carefully, the orange patch, okay, so that patch is actually extending from this decision boundary towards the classes. So it's extending towards left, and it's also extending towards right. And it will keep extending unless it will touch like any training sample. So in this case, it's touching this sample. And in this case, it's touching this sample, which means that this yellow or this orange patch over here, that's the area where you don't have samples from either like the solid dots or the hollow dots. Okay, and this space is actually called margin. Okay, how much bandwidth or how much space you have left between the decision boundary and the closest sample for either of these classes. Now the goal is we want to maximize that margin, and that's what this maximal margin classifier will do. The name says it all. All right. Now that was one. If you look at this one, this looks pretty cool, right? Again, the center line here will be the decision boundary, which will always be at the center of this patch. And this is like the closest point. Okay. And again, this is the closest point. This is the closest point from the decision boundary. And in this case, you can see like the margin is much bigger as compared to this. So in maximum margin classifier, what we want is we want to maximize these margins. And that's what we optimize when we train our classifier. As I said, like training is involved here. Okay, so this is kind of also like a very simple form of, you can say, linear support vector machine. Again, we'll talk about that later. There's some confusion in nomenclature, but we'll try to clarify that. Okay, so the black line over here is your classifier, and the boundaries of these margins, these are called support vectors. Okay, so these support vectors are something which are exactly touching your training samples. Okay, so the idea is you want to maximize the distance, or you can say like the perpendicular distance between your classifier, or you can say like the classifier line you have, and the support vectors. Okay, so, and again, let's see like how that can be done. Again, we won't dive too much into that, how we can optimize those equations, just the intuition, because again, optimization, that's like a separate topic, and it will take a long time. So don't worry about if you don't understand the actual optimization process, but try to understand the high level idea. Okay, so these SVMs, I think they were developed, I think in 1990s, and since then they were like very popular until 2012, after which deep learning actually just swept them out. Okay, so there's an interesting story as well. So during these 1990s, like researchers were also working on developing neural networks, right? But these support vector machines, they were working really well, and they work really well even today. Okay, it's not that they're not working so well. So they are very, very powerful. And in some of the cases, like where we don't have a lot of data, still I think SVMs can outperform your traditional CNNs, but that's like a separate topic. Let's not go there. So the story is like in 1990s, researchers were working on both these support vector machines and also neural networks. But again, back then we didn't have like a lot of data. We don't have a lot of computation power. So neural networks were kind of going very slow. But SVMs, we don't need a lot of data. right? We can quickly train, we can just optimize your simple parameters. And they really work like very well in all the scenarios. And I think that's the reason like the deep learning era, which we are seeing, it was kind of delayed, because we might have seen that pretty soon. We waited until 2012, and the reason is like the support vector machines. So after 1990s, like 20 years after that, like everyone was just focusing on support vector machines, a lot of research. But then again, they are suddenly gone after 2012. So now everyone is focusing on deep learning. But I think now it's time to actually go back, and somehow I think there is a way to combine both of these together. We are looking into some of that in our research as well. But still, I think deep learning, because we have data and computation power, so it's kind of questionable, like whether we should go back or not. But anyways, so that was the story. Now, the timeline, how it goes is, first we had like maximum margin classifier, which we'll talk about first. And all of these are kind of related, because in all of these, we are trying to learn this decision boundary, where we're trying to maximize that margin. Okay, then we have a support vector classifier, and then we have support vector machines, all of these related. So we'll try to cover each of these in three separate segments. So let's first go to like a max margin classifier, which we briefly covered earlier. Okay, so the idea is, what we do, we try to learn this hyperplane. And this hyperplane, in case of your Euclidean space, which is two-dimensional space, it's going to be a 3D line, or you can say like a plane, right? A 3D plane. And okay, no, sorry. So if it's a 2D Euclidean space, then you just need a line, right? So that's the first point. And it will be a 1D line, right? You will need two parameters for that. If it's like a three-dimensional space, the hyperplane will be like a 2D plane. And similarly, if you have a p-dimensional space, which is usually the case because your features are most of the time in high-dimensional space. So you will need like a hyperplane which will have dimensionality p-1. And that's all what we need to learn to get this maximum margin classifier. Okay, so the general equation for your hyperplane can be represented as this equation over here. Okay, so all these coefficients are parameters, and these x1, x2 are like corresponding to different dimensions you have in your space. For example, if it's like a 1D line, which is in two-dimensional space, something like this. As I said earlier, for a line in 2D space, you just need two parameters. The intercept, so this β0 is the intercept. Okay, so that's the first parameter. And then you need the slope of your line. So this β2 is actually, it's not exactly the slope, but you can say, okay, this could represent the slope, because you can compute slope using this parameter. So it controls your slope. Okay, so in case of 1D line, you only need these first two terms, β0 plus β1 times x1. And that will define your one-dimensional line. And similarly, if you increase the dimensionality of your space or your features, you can keep adding more dimensions. But in general, this will be the representation of your maximum margin classifier. That's how the hyperplane will really look like. Okay, so yeah, why we have x1, x2? Okay. So yeah, so this equation will, yeah, I don't know why we have x2. I think this should be in two-dimensional, right? Because for one dimension, you don't really need like both of these. But anyway, so that's fine. This is the general formulation, and you know like how it will look like in n-dimensional space. It's just a hyperplane. All right, so now what will happen, what you're going to learn is, you will have your training samples. Let's say if it's a binary classifier, you have blue dots, you have these purple dots here, and you're going to learn this line, or you can say hyperplane. And there are many, many possibilities. So we want a hyperplane which will maximize these margins. Okay, so the distance between this hyperplane and the support vectors should be maximized. All right, so what we can do is we just try to maximize this margin. All right, and these are the constraints, like your training samples. Okay, so let me go over one more step. So if this is a hyperplane, then if we use this training sample, if you try to put on this equation, it will give you negative value. All right, and if you put like these points over here or these coordinates, it will give you positive value. So what we want is, we want to satisfy that constraint, that if we have like this margin over here, it should always be towards the right. So all purple dots should be towards the right, and all blue dots should be towards the left. Okay, considering that constraint, so that's the constraint which we have here. We are just placing all the training points in the equation of your hyperplane. So they should be like greater than m. So m is your margin, because they are that distance away from the decision boundary, because m is your margin. Okay, as I said, if the point is directly on this plane, the value will be 0, but we want that value to be m. Okay, so that's what we are optimizing. And then once you have this equation, you can just use any optimization technique to actually find these values. So the values you're looking for is all these betas, which define your hyperplane. Okay, so that's fine. And as I said, don't worry about like how to do the optimization. That's like a separate topic altogether. Just try to understand the concept of how this classifier works. Now let's try to figure out like whether this kind of classifier will be robust towards noise or not. And that will motivate you to go further and study, let's say, the support vector machines. All right. Now, let's say your after optimization, you found this as your hyperplane, and you can see that it's kind of maximizing the margin, right? The distance from this purple point and this blue point, that kind of is the maximum. But now let's say you have another testing sample, which is at this point. So this is kind of a corner case as well, because if it has to be blue, it should not be close to purple, right? But let's say if it is there, then this dash line, which we actually learned using that optimization, will completely fail, because it will say this is a purple dot. So in this case, you can see this hyperplane is actually working. Okay, in this case, the blue is actually on the other side. So you can see that if you have more and more samples along this decision boundary, then your classifier is actually not very robust to those kind of samples. Because this is a very drastic change, like going from this classifier to this classifier. You can see like the slope actually changed a lot. Okay, so it's actually very sensitive to what kind of samples you will have in this boundary. And of course, it's not sensitive to like points which are far away from the boundary, which are kind of like simple or trivial points. Okay, it won't change like. So if your point is beyond like these boundary points, which are kind of, you can say like at the frontier, then the classifier will never be affected. You can have as many points as you want. So today we have, again, we'll continue from last time. We were talking about classification. And again, this is like the first half of classification. So the first lecture, and we were talking about max margin classifier. And I think you will also, you will have like, you have a programming assignment on classification, and that's using nearest neighbor, which is kind of a simplistic format. So let's continue on that. So today we'll have this new segment, which is support vector machine. And again, this is going to be like on top of what we discussed last time on max margin classifier. Okay, so let's try to understand like why we need support vector machines and why maximum margin classifier was not sufficient. So let's try to understand this scenario. In this case, we have two different classes. We have blue and we have purple. All right, and again, this is projected on 2D space. And of course, we can generalize this to a multidimensional space as well. But in this particular scenario, if I have to build like a classifier, or let's say like linear classifier for sake, then it doesn't matter like what kind of boundary I draw. I will never be able to separate these two classes. Okay, so this is kind of a spatial case where your your training samples are actually not separable. And the reason is, if you look at like these purple dots over here, this one and this one, so they're kind of in middle of these blue dots. And same is the case with like, you can select the blue dot over here. It's kind of very close to the blue dots. So no matter what kind of boundary you draw, what kind of straight line you draw, you will always have error in your training sample. All right. So then how we can handle that? So one easy solution is we kind of relax the condition that your classifier should be perfect on the training data. So we relax that condition and we allow some kind of errors. Okay. So in that case, what will happen is, if we draw like your decision boundary, and then of course we'll have the margins. So this is like the starting point for your support vector machines. And these are your support vectors. So this was like a cleaner case when your classes were clearly like separable. And if you have to train like your support vector, max margin classifier, you will get something like this, where this will be the decision boundary, which is represented by this equation here. Okay, you need like two different parameters. And the margins will perfectly touch like these extreme points. For example, this red dot here and green dot here. And the condition is none of the samples from either of these two classes should actually be inside these margins. Okay, so that was the condition, and that's possible when you have a cleaner scenario. But if it's a non-separable case, then what we can do is we can actually allow some of these samples to cross these boundaries. Okay, so what we do, we not just allow like these samples to cross the support vectors, but we also allow to cross the decision boundary itself. So in this case, you can see that you have a red dot over here, which is lying completely like towards the green dots. So in case of max margin classifier, I mean, you will not be able to come up with a solution because you cannot draw like a linear line separating these two. So, but in this case, if you allow this kind of error, then what will happen is, even if your samples are non-separable, you will be able to come up with a decision boundary. And then what's happening here is, for some of these samples, you will compute like this error term. Okay, so for example, if this is your support vector, then you will compute like the distance between this support vector with this sample, which is actually crossing the boundary. So in this case, you will see like three different red dots are actually crossing the boundary. The first two are crossing the support vector. So you have like this eta1 and eta2 as error. And this red one is actually even crossing the decision boundary and also crossing the other support vector. So you have like a very big error here, which is eta5. And similarly, you have errors for like some of the green samples here. Okay, so this is crossing the support vector. That's some error. And again, this one is again crossing the decision boundary. So you have a bigger error. And what you do is, then you try to sum up all these errors. All right, so that's kind of error you will have in your training samples. And then you have like some kind of constraint. You say that you will have some kind of total budget, and whatever error you have from these samples, that should not be greater than this constant. Okay, so that's kind of your allowable error. And with that constraint, you can actually find this equation, and then again your support vectors depending upon what your margin is. Of course, like all that optimization is not going to change. The only constraint you have is this new one, which will compute what kind of error you have for each of these samples. All right. So this is called a support vector classifier, and the only difference between your max margin classifier and support vector classifier is, in max margin, you don't have that error. None of the samples can cross the support vectors. None of the samples can cross the decision boundary. In support vector classifier, you might have some samples which are crossing your decision boundary or your support vectors. Okay, so that's the only difference. So this, you know that you first try to maximize this margin. And these are the parameters, like the parameters of your equation or your plane, depending upon like what kind of dimensionality you have in your data. And then you have additional terms, like these are error terms. So for each sample, you will compute this error. And for most of the samples, the error will be 0 because they will be like in the right side of the plane, right? But these will like come into account when some of the samples are actually trying to cross the boundary. So you will have, again, this is the same condition. You are trying to minimize like the parameters of that equation. So don't worry about this. All this is your max margin classifier. And again, this is also coming from your max margin classifier, because what it's trying to do is, so this is your learned equation. Okay, so your beta 0, beta 1, all these are your parameters. P will depend on like what's the dimensionality of your space. And yi is just a sample. Like, so for each sample, you will, yi is actually your class label. So it will be either +1 or -1, depending upon which class you have. So each sample you will put in this equation, and then it will give you like some kind of sign. Either it's positive or negative, depending upon which side of the decision boundary that point lies. And then you will try to maximize this margin, right? So instead of just sign, you look at this value, like how far that point should be from the decision boundary. So that's the margin M. And this is the additional term, the error. So for each sample, you will have this kind of error. So this is the additional term you will have in support vector classifier. And later you will see that you have a lot of hyperparameters when you try to train your support vector machine or support vector classifier. And one of the important parameter, if you have trained like these models before without understanding what it is, so you might have seen like this parameter, hyperparameter C. Okay, so that C actually means this allowable error you can have in your training samples. Okay, and again, this is a hyperparameter you will set when you're training your classifier. And again, as you change your budget for this value of C, your decision boundary will change and your support vectors will change. Okay, so this is like a non-negative tuning parameter. Of course, non-negative because you want like some allowable positive error, right? If it's negative, then it's same as your maximum margin classifier, because you're not allowing any error. All right, so that's the difference between maximum margin classifier and support vector classifier. And so again, this is just showing you one example where you can see like you have again two classes, blue and purple. And in this case, they are clearly separable, right? And in this case, you can see this is the decision boundary and these are your support vectors. So this 0.1 and this 0.8 are actually crossing the support vector, but still they're not crossing like your decision boundary. Okay, so that's kind of an easy case. The second scenario here, you can see like they're crossing the support vectors, but again, some of the samples are actually crossing even the decision boundary. Okay, so in these samples, this is like just one sample solution you can have. So this will be like your decision boundary, and these will be your support vectors. And it's just showing that you will have allowable samples on the wrong side of your plane. Okay, so now let's try to understand like the effect of C, which is the parameter in your support vector machines, how that changes like the decision boundary, and how will that change the support vectors you will have. And again, this is like all four are corresponding to the same training data. And in the first, you have like a very large value of C, which means you are trying to allow like a lot of samples which can cross the boundary, which can cross the support vectors. So in that case, this is the decision boundary, which is kind of learned. And if you will look carefully, I mean, this looks fine, but again, there are a lot of like these blue dots right over here, which are kind of on the wrong side of the decision boundary. And if you pay attention to like these blue dots, none of these dots are actually on the right side of the support vector. All of are like in the wrong side. And same is the case with the purple ones. So it means like for this particular training data set, you need like a smaller value of C. You're actually allowing a lot of error. You're relaxing a lot. Okay. And this, again, these three are like, as you try to reduce the budget C. And again, then you can see like your decision boundary is actually changing. It's kind of rotating as well. It's shifting. It's moving towards the purple side. And now some of the samples are actually on the right side of the support vectors. Some over here are also on the right side of the support vectors. Okay, so again, if you reduce it further, you will get something like this. And again, it's hard to say like which of these is correct. Of course, this is wrong. We can clearly see this is like the value of C is too high. But the other ones, again, this we can say like it's too high because most of these samples are within the margins. But between these two, it's hard to say like which one of these is better. And that's why we have like when you train your models or train your classifiers, you have three different splits. You have training split, you have validation split, and then you have testing split. So in this scenario, what you're going to do is you can actually set some value of C, and then you will evaluate that model on your validation set, and then you can just compare those two. And if like this C is actually better on validation, you will pick this. If this one is better, you will pick this. And whatever that model is, then you will use that model with the final selected C on the test set. So this is, I think, something interesting. And SVM, they do work, and like optimizing these parameters. If your data set is not too huge, it's pretty fast. And I myself has done this like a lot of time earlier when there were no neural networks. And what we used to do is we actually just used to do grid search. So we'll start from like a very high value of C and then keep incrementing it or keep decrementing it with small values. And then we'll kind of explore all the space and then just test all those models on the validation set. Okay, so that's called, you can say, you're trying to like fine tune your parameters to determine like a better model on the target data set. Okay, and it is required because all data sets are different. And when I say all data sets are different, so, and there are a lot of different ways they can be different, but what we're interested in here is like this data set is like what we're interested in, what's the distribution of the samples like in this embedding space. Okay, so that's the unique property of this data set. And again, if you have a different data set like this scattered plot over here might look different. And that's why we need to hypertune or fine tune these parameters. All right, so that was about the parameter C. Now, another interesting aspect is, until now we have seen that your decision boundary is always linear. And that's kind of restrictive, right? Why it has to be linear? It could be like a curve or something. But then the issue is when it's very hard to learn like those curves. And we will discuss like a very clean solution where you don't have to learn those curves. You can still use your linear classifiers, but it's kind of a trick which will lead you to like from support vector classifier to support vector machine. All right. So let's try to understand how that works. So in this case, this is the data set, and these are like this is the sample distribution. And you can see like if you try to learn like a linear boundary, it might look something like this. So the dashed line is the decision boundary, and these are your support vectors. And it's kind of fine, but still like it's kind of making error, right? On these, let's say on this sample. And again, this sample and this sample, it's kind of on the boundary. One is like on the wrong side. So this is also on the wrong side. And whatever, how hard you try, sometimes it might not be possible to actually separate these two by just using a linear boundary. Okay, so one solution could be you can try to learn this kind of curve. Okay, so I mean, as I said, it's not impossible, you can do that. But then the issue will be, then you're kind of trying to overfit to this training data. Okay, so what might happen, let's say you learn this curve, then what if your testing sample is actually at this point and all your testing samples are at this location? I mean, your classifier will completely fail, right? Because all those testing samples will be on the wrong side of the boundary. Okay, so that's what like is the limitation of your support vector classifier. And that's just one scenario where the boundary is not linear. The other interesting case is, what if like they are not even connected? Right? For example, you could have a data set which is something like this. If you look at the distribution, and the blue dots over here and the blue dots over here, they actually belong to the same category. But in the embedding space, they are actually far away. Right? So in between, you have this purple class. Now, I mean, how hard you try, I mean, you can for sure not like create a decision boundary which is linear and use that as a classifier to solve the classification problem on this kind of data. Okay, so if you try to learn, let's say, a support vector classifier using this training data, you might get something like this. But again, it might work for some samples. Let's say your accuracy could be, let's say, what, 40%, 50%, depending upon like how many of these samples are actually falling in this side. And so all these purple ones are correct and all these blue ones are correct. But then you might have a lot of purples here as well and a lot of blues here as well. So you might get, let's say, 40%, 50%, but it can never go beyond that. Okay, because it doesn't have that capability to separate like this kind of space. So now, if you think about this, one easy solution could be if your decision boundary looks like a circle. Okay, then that seems like a very good classifier for this kind of data. And then you can say that whenever a sample is inside that circle, it's like purple. Outside the circle, it's blue. Okay, so let's see see how we can do that. And that will lead us to like nonlinear SVM, and that's also called support vector machine. So what will happen is we'll still learn like your linear boundary. Okay, it's not that we're trying to learn nonlinear boundary, but still like this is the trick. It will work as it is actually nonlinear. Okay, so I think this is a pretty cool idea. Bear with me, and we can come back to this again if you don't understand this. Now look at this Euclidean space here. So these are all the samples coming from red class and blue class, and you can clearly see that whatever linear boundary you try to draw, you cannot separate these two classes. But you can have a non-linear boundary. Let's say this circle, and this circle can actually very easily differentiate between blue and red. Okay, now what you can do is you can project all of these points. So right now they are in two-dimensional space. What you can do is you can try to project them into three-dimensional space. Okay, and how we can do that, I mean, you can use any function to actually project this to three-dimensional space. And I will give you like one example how you can do it. So this is your dimensionality of the source domain. So in this case, two-dimensional. What you do is you come up with a function which is actually going to project each of these points to a high dimensional space. So in this case, we can go from two-dimensional to three-dimensional. And let's say it looks like something like this. And one simple function for the psi for this particular case could be, let's say, a square function. So let's say you just square the x and y values. So what will happen? These are like bigger values, okay, in terms of like, so all the points which are outside this circle, they will have bigger magnitude, right? It doesn't matter whether it's in the x direction or in the y direction. And even if it's like on this side, if you just look at the magnitude, it's going to be bigger. It will have a negative sign, but still it will be bigger. And that's the reason they will be like lying outside this circle. Okay, so for example, let's take an assumption. This is the origin 0 cross 0. And let's say this point is 1 cross 0. This is 0 cross 1. Again, it will be negative 1 and 0. And this will be, let's say, 0 and negative 1. Okay, so all the points inside the circle, wherever they are, it doesn't matter. The values will be between 0 and 1 for both x and y dimensions. And similarly, all the points which are outside the circle will have values greater than 1. Mostly, this is like a corner case, just ignore this. But more or less, they will have values greater than 1, both for x and y. Now, if this function is, let's say, square function, now what will happen is all these negative values will become positive because you're taking a square. And if the values are bigger, then the square will also be bigger. Okay. So that way you are actually projecting this into three-dimensional space. So you add one more dimension here, let's say z. And then you can see that all these points are actually going away from the center. So this was their origin, and all they are like just flying away. they will move away, right? You can just get like XY values for those. And similarly, all the red points, again, you will square, they will become positive, but still they will remain small. They won't be as big as blue. Now, once you have done that, then what you can do is you can actually come up with a linear plane which can separate the red dots from the blue dots. Okay, so this is also called like a kernel trick, and the idea is to just learn this kernel function which can project your points from small, like a very low dimensional space to a high dimensional space. And it is interesting because what it's trying to do is it's trying to project in high dimensional space, but also making them linearly separable. All right, so that's called support vector machine. And so that was a kernel trick which we just discussed. And again, you can learn like all of those, lot of kernels in your support vector machines. We are not going to go into detail because I think just that part was really interesting, how you actually do that. So in this case, you can actually learn these nonlinear boundaries. That's one example. Okay, so in this case, you're trying to learn two different nonlinear values. That will do the trick. But again, if you project that like to a high dimensional space, you can just learn like one kernel, and you don't need these two different classifiers. Okay. Now, so that was SVM, and again, there is a lot to SVM than that, but that was the main crux. But don't worry about like if you don't understand other things. I think in some of the machine learning courses, you will have that opportunity. But again, you will know that okay, why SVM actually are better than your support vector classifiers. Now, the question is, again, even if we have this trick, we are just differentiating between two different classes. But in reality, I mean, you most of the time you will have multiple classes, right? So how you can do a multi-class classifier using SVM? And till date, we don't have very clean solution. The only solution we have, we just train multiple SVMs as binary classifiers. And I think we discussed that trick when we started this lecture. So what we do is for each class, we train a binary classifier where we treat that class as positive and all the other classes as negative. And we do that for all the classes you have in your training data. Okay. So this is called like one versus others. And this is exactly what we discussed. And then you can have one versus one as well, where you just select like pairs. Okay. So for each pair of classes, then you can learn this classifier. Mostly like I think this is more useful and generalizable. So some good things and bad things about SVM. Of course, like they actually work really well in any kind of data, and there are a lot of packages which are available out there for SVM. And as I said, like this was one of the reason why the deep learning era was delayed. So starting from 90s, early 90s to like all the way 2010, 2012, like SVM, everyone was actually researching on this. So there's a lot of research and a lot of available code out there. The idea of this kernel-based framework, the transformation, that is actually very, very powerful. It's very flexible, and it allows you to learn like very, very complex decision boundaries. Because how complex the decision boundary is, if you just try to project that to a high dimensional space, that might turn it to like a very, very simple boundary, just a linear boundary. Okay, so that idea is very powerful. It's just like it was used in SVMs, but in general, I think that idea is very interesting. And I think so far I haven't seen like that kind of idea being incorporated into neural networks. If one can do that, I mean, I think that will make the neural networks even powerful. In a way, I mean, they might be doing it, but we haven't seen that done explicitly. And I will say that's like a very, very challenging research question as well. And as I said, in practice, SVM, they work really well. It doesn't matter, even if you have a very small training set, they will try to learn the boundary pretty well. The bad side is if you have a lot of data, then it's very hard to actually train these classifiers. Okay, they becomes like computationally inexpensive because like we have to solve that optimization problem, right? So if you have a lot of samples, it's not that trivial. The other limitation is like if you have multi-class SVM. I mean, we do have a trick to do it, but again, that's not like a very nice solution. And like you have seen neural networks, right? So it does it very effectively. I mean, you can have 2 classes or 1,000 classes. It doesn't matter. So yeah, that's the other issue, like computation or memory concern. If you have a lot of samples, it's very difficult to train these.